Hey guys, this is Mrs. Keith, and we're going to do notes today over 1.2. It'll include the parent functions and piecewise functions. So we're going to focus first on parent functions. These are functions that you need to be very familiar with. You've been studying them since Algebra 1. You need to know what their equation is, what the name is that matches that equation, what the graph looks like, and then critical attributes like what the domain and range is, as well as some other critical attributes. So this first one is the linear function. Looks like this when you graph it. Its domain is all real numbers. We'll write it like this, negative infinity to infinity. The range is also all real numbers. Critical attributes. You have an x and y intercept at 0, 0. Also, if you'll notice, as you read this graph from left to right, it's going up over the entire domain, and so it's considered an increasing function. It's also considered an odd function. What makes it odd is the fact that it reflects about that origin. So if you'll notice in diagonal quadrants, you see the exact same image. So in quadrant 1 and 3, we see the same thing. Okay, the next one is called the quadratic function, and it looks like a U shape. Its domain is all real numbers, so negative infinity to infinity. Its range, it stops at 0. It doesn't go lower than 0 on the y-axis, so it goes from 0 to infinity. It includes 0. That's why we have a bracket there. It also has an x and y intercept at 0, 0. And it's considered an even function. It's even because if you'll notice, it reflects across the y-axis. Anytime it reflects over the y-axis, it's an even function. Okay, the next one is the square root function. And it looks like this. It's actually the inverse of the quadratic function up there. Its domain, it doesn't go any further to the left than 0 on the x-axis, but it's including 0, so it goes from 0 to infinity. It's all the x's greater than 0. The range is all the y's greater than 0, so 0 to infinity as well. It also has an x and y intercept at 0, 0. And it's neither even nor odd. You'll notice it does not reflect over the y-axis, and you don't see the same image in diagonal quadrants, so it's not even or odd. Okay, I'm going to scroll that up. Okay, this is called the inverse function, or sometimes we call it the rational odd. It's considered rational odd because it's just 1 over x. If it were 1 over x squared, it would be rational even. One of the critical attributes about this function is that you have a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis. So when you graph it, it looks something like this. Now, if you'll notice, you're using all of those x's except for where the x-axis is. Where the y-axis is. So your domain goes from negative infinity to 0. It does not include 0, and then union 0 to infinity. So what that's basically saying is that you're using all real numbers except for x equals 0. The range is going to be the same thing. You're using all of your y's except for 0 because that's where an asymptote is. Okay, so a critical attribute is the fact that you have a horizontal asymptote on the x-axis. That equation would be y equals 0. You also have a vertical asymptote on the y-axis, and that equation is x equals 0. All right, next we have the exponential function. This one also has an asymptote. It's, again, the x-axis, but it only has one asymptote this time. It looks like this when you graph it. It has a y-intercept right there, so it has a y-intercept at 0, 1. Has a horizontal asymptote at y equals 0. Its domain is all real numbers. Your range, it doesn't go below that asymptote, so it's going to be from 0 up to infinity. Now notice this time I used a parentheses because it can't touch that asymptote. It won't include 0. Okay, the next one is the logarithmic function. These two are inverses of each other. So instead of having a horizontal asymptote, you have a vertical asymptote. a vertical asymptote at x equals 0. You have a x-intercept instead of a y-intercept like the other one at 1, 0, and it approaches that asymptote here, and it looks like this. So its domain, it doesn't go anywhere to the left of that asymptote. So it goes from 0 to infinity, does not include 0 because that's an asymptote. And its range is all real numbers, so negative infinity to infinity. I forgot to say, these two are both neither even nor odd. Both of these are neither even nor odd on either one of these. The first, 1 over x is an odd function. Okay, y equals x cubed looks like this. It's called the cubic function. Its domain is all real numbers, so negative infinity to infinity. The range is all real numbers, so negative infinity to infinity. It has an x and a y-intercept at 0, 0. And this one's considered odd because if you'll notice in diagonal quadrants, you have the same image. It reflects about the origin. Okay, let's do the next one. Okay, the next one is the cube root function. It's an inverse function for the cubic, and it looks like this. Its domain is all real numbers, and its range is also all real numbers. It has an x and y intercept at the origin, and it is an odd function because if you'll notice in diagonal quadrants, you have the same image. It reflects about the origin. The next one is called the absolute value function. It looks like a V shape. If I can make that, sorry. Its domain is all real numbers. Goes forever to the left and right. Its range, it doesn't go any lower than 0, but it does include 0, so it goes from 0 to infinity. It also has an x and y intercept at 0, 0. And it's considered even. Again, what makes an even function is the fact that it reflects over this y-axis right there. Okay, this one you may be less familiar with. I'm not sure that you learned this in Algebra 1 or Algebra 2, but it's called the greatest integer function. And it looks something like this. You're going to have a closed-in circle here. Then you're going to use all of the x's up to 1, and then at 1 it's going to be an open circle. And then you're going to have a closed circle here. That's what makes it a function. You can't have x's that repeat. And then it'll be all of those x's up to a point. Then you'll have a closed circle, all of those x's up to a point. And we'll talk more about it on the next page, but this is what it looks like. Its domain is all real numbers. You use all of the x's. The range, though, is only going to be the set of all integers. And the way we write that in a mathy way is we say y such that y is the set of all integers. And this is z-looking thing that has like a little double thing right here in the middle. That means integers. So basically what I've just said is that y is the set of all integers. Okay, so you have an x-intercept. You have a lot of x-intercepts, actually. All of these right here are considered x-intercepts. So they go all the way from 0 up to 1, but not including 1. You have a y-intercept at just 0, 0. If it's a function, you can't have more than one y-intercept. And it's neither even nor odd. It doesn't reflect over the y-axis, so it's not even, and it doesn't reflect about the origin, so it's not odd. All right, let's focus a little bit more on that function. Okay, going to the next page, I'm going to read this aloud with you. And we denote it using this symbol right here. That lets me know that I'm using the greatest integer function. And it is defined as the greatest integer less than or equal to x, and it has an infinite number of breaks or steps, one at each integer in its domain. So what happens is that when you're doing all the x's from 0 up to 1, the lowest x value from 0 on a number line, if you think about it like this, from 0 to 1, the lowest x value is that 0 right there. So the y value is going to be 0 for all of those x's. And then let's go from x values from 1 to 2. So if you go from 1 to 2, the lowest x value, if we go from 1 to 2, the lowest x value is going to be that 1 right there. So the y value is 1. And then we'll do the same thing. It's just a step each time. Now notice I have open circles and closed circles. Like right here, there's an open circle and a closed circle. That's what makes it a function. You can't have x's that repeat. X is same way. When x is -1 to 0, the lowest x value is a -1, so the y value is -1. So the same step function, it goes infinitely like this. We just have this much of it to graph. Okay, so an example of a type of problem that you might see, we'll say something like, we'll use that same symbol. And I forgot to talk about the domain and range. Sorry about that. The domain, again, is -infinity to infinity. The range is the set. Y is the set of all integers. Okay, so an example of a type of problem that you might see is we'll use that same symbol and we'll put a number in here like 2.3. And if you think where that number lies on the number line, so like here's 0, here's 1, here's 2, and here's 3. 2.3 lies somewhere about right here. That's about where 2.3 is. So if you think about that number, you're going to choose the x value, the greatest integer less than or equal to that x value. Well, the greatest integer less than that x value is 2 right there. So the answer to this would be 2. All right, another example would be, let's say we did a -1. Let's do like -1.6. So think about it on a number line. We have 0 here, -1 here, -2 here. So -1.6 lies about somewhere right there. So the closest integer less than that number is a -2. So the answer to this would be -2. All right, let's move on to piecewise functions. Okay, piecewise functions. Basically, when you're graphing piecewise functions, what you should be thinking about is that you're graphing more than one function on the same graph. And again, you want to keep it a function, so you've got to limit your domain. And we do that using this notation right here. This is telling you what you can graph, what domain you can graph each function over. So this first one right here, we're graphing a linear function. I know it's linear because we just have a plain old x. And you're going to graph it where x is less than or equal to 1. And then this one, because of that x squared, we're going to be graphing a quadratic. It's going to be graphed where x is greater than 1. Okay, we also want to make sure you remember your inequalities things. So when you're graphing an inequality and it has just the less than or greater than, like these right here, you use an open circle. When it has the less than or equal to or the greater than or equal to, you use the closed circle. Okay, so this first question says, what does it mean when x is less than or equal to 1 is written at the end of the first equation? So what that means is that you will graph the linear function for all x's less than or equal to 1. And it will have a closed circle at x equals 1. And then what does it mean when x is greater than 1? You're going to have a quadratic function. Graphed for all x is greater than 1 using an open circle. At x equals 1. All right, let's see what our table will look like. I'm going to Scroll this up just a little bit, which will mean that this will probably erase. I'm sorry. Okay, we're going to graph the first equation that they have written up here in our problem. It wants us to do all x's less than or equal to 1. And so notice those are the x's that we've chosen right here. And basically you're just plugging in 1. If I do -1 plus 1, I get 0. 0 plus 1 is 1. Negative 1 would make it positive 1 plus 1 is 2. And so this is your table filled in. Then on the next one, you're going to focus on all the x's greater than 1 for the equation y equals x squared. So when you plug in x is 1, you get 1. When you plug in 2, you get 4, and then 9. I usually put like either a closed circle. I mean, where my function gets separated there is at x equals 1. I need this one to be a closed circle, so I usually will put a little closed circle there, and I'll put an open circle on this one just to remind me when I'm doing the actual graph. So I'm going to graph that. When x is 1, my y is 0. At 0, 1, I have a point. So this is a linear equation that goes this direction for all the x's less than or equal to 1. And then here we have a quadratic equation that gets an open circle. And we have one way up here at 9. So it looks something like this. So that is your piecewise function graphed. All right, let's scroll down just a little bit. Okay, notice we have used every single x, so our domain is going to be all real numbers, or negative infinity to infinity. You could also just say all real numbers. My range, though, isn't going to go any lower than where y is 0. This is the lowest y value that we have. And so it's all the y's greater than or equal to 0, or you can say from 0 to infinity. All right. And then they want us to evaluate a few. I have to scroll down again. Okay, I'm not going to scroll down much further because I don't want to miss out on the graph. We're going to evaluate each of the following. This is saying f of -2. Now remember, for this particular function, these were all the x's less than or equal to 1. And so we would use the -2 for this equation. So I'm going to be plugging in a -2, and for that x, so -2 plus 1 gives me 3. So, which matches what we put right here. F of -1 is going to be 2. Again, we could plug it in if we wanted to. -1 plus 1. You'll focus on that equation because that's the one for x is less than or equal to 1. And so we get 2 for that one. F of 1. So you've got two different f of 1s. This one is the one that we can actually use because we can use the 1 on this one. It's less than or equal to 1. So our answer would be 0. And then f of 2 is going to be 4. That goes with this one right here. All right, let's do the next page. Okay, on this page, we want to focus on what continuity is. It's either continuous or discontinuous. If it's continuous, basically, as you're drawing, you never pick up your pencil to finish the drawing. If it's discontinuous, you have to pick up your pencil at a certain point and then finish the drawing. So we have 3 different types of discontinuities. We have removable discontinuity. An example of a picture that you might see is when you have a hole in the graph. So when you did rational functions last year, you might have had a hole that you had cancel out. And you might have graphed that actual point right there. So that's a removable discontinuity. You have a part removed out of that graph. A jump discontinuity is where you jump to finish it, kind of like on our last example. So if we look at a picture, if you have like a line here and a quadratic over here, this part right here represents a jump. You had to jump in order to finish the graph. Take your pencil off the paper to finish it. An infinite discontinuity is when you have an asymptote. So when you have something like this, and let's say you have an asymptote right here, and so you have a graph that looks like this. That's called an infinite discontinuity, where you have to pick up your pencil to finish the graph, and where that's happening is at an asymptote. Okay, let's do some more examples. All right, using my parent function knowledge that we talked about earlier, I know I'm going to be graphing a quadratic and an absolute value function. So we're going to do the quadratic part here and the absolute value part here. All right, if you'll notice, we're kind of focusing around x being 2. So I'm going to put that kind of in the middle. And I'm going to do some x's less than that. And I'm going to do some x's greater than that. For y equals x squared, those are the ones that are less than or equal to 2. So you don't want anything past that on that graph. For the absolute value function, you want all the x's greater than 2. So you don't want anything less than that. So those are the ones we're going to focus on for each of those functions. So when x is 0, when I plug that in, I get 0. When x is 1, I get 1, and then 4. For the absolute value function, when I plug in 2, I get 0. And then when I plug in 3, I get 1, and when I plug in 4, I get 2. Okay, remember at 2, that's where that should be the discontinuity. For the x squared, this is where you have x is less than or equal to 2, so it's going to get the closed circle on that one, and this one's going to get the open circle. Just a reminder for that. All right, let's graph that. So y equals x squared. We have a closed circle here, or just a dot, a point actually, and then 1, 1, and then at 2 we have a closed circle at 4. And then this is, we're graphing everything to the left of 2. So if you'll remember, this is a quadratic. So at x equals 0, that's our line of reflection. So you should have symmetric points on either side of that line. So this should be your graph. And it continues on forever because it says less than or equal to 2. So you put that arrow there. Then for the absolute value function, at 2, 0, we have a point, and it's an actual open circle. And then at 3, 1, we have a point, and at 4, 2, we have a point. And remember, that's an absolute value function that's just been shifted to the right 2 units, and so it's a V shape, but we're only getting this side of the V shape. Okay, so that's what our graph looks like. My domain uses all real numbers, so negative infinity to infinity. If you'll notice, your range isn't anything lower than 0 for the y's, but you do include that 0, so it's going to go from 0 to infinity. F of 1, that's going to use the x squared graph, so f of 1 would be 1. F of 0, that's going to use the x squared graph, so that would be 0. F of negative 2, that's going to use the x squared graph, so that would be 4. And f of 3, that's going to use the absolute value of x minus 2 graph, and so that's going to be 1. F of negative 7, that's going to use the x squared graph, and so that's going to be 49. This is definitely discontinuous, and the type of discontinuity that it is a jump discontinuity. All right, let's do the next example. Okay, for this last one, they want you to write the equations of this piecewise function. So you're going to have 2 equations to write. If you'll notice, right here is where the discontinuity happens. So we're going to end up having our domain restricted there at x equals 0. So the part on the left will be all the x's less than or equal to 0. The part on the right will be all the x's greater than 0 because it has an open circle on the part on the right. Okay, the part on the right is pretty easy, it's pretty easy, sorry. This is a linear equation. It could also be absolute value if you wanted to make it that way, but we're just going to say linear here. It would be y equals, if you'll notice you have a slope of 2, you rise 2 and go over 1. It's a positive slope, and your y-intercept is at negative 4, so it's going to be 2x minus 4. So that's your second graph. The first graph is a little more difficult. This is quadratic. You can kind of see that U shape. So remember your parent function for the quadratic was y equals x squared. And if you think about the y equals x squared graph, when you do your table, you have a point at 0, 0. I'm going to choose some negative values because this goes to the left of 0. So at x equals negative 1, you should have a y value of 1. Well, this particular table or graph, when x is, we have the 0, 0 point, but then the next actual point that we have is right there. So when x is negative 2, the y value is 3. So what I did to go from the first table to the second table is I multiplied, if I focus on this point right here, what it became, I focused on multiplying the x's by 2 and multiplying the y's by 3. So if you think about that equation, I changed my y's by 3, and I changed my x's by 2. So if you think of that parent function, remember when you're doing transformations, you have it in the form y equals a times b of that x squared. All right, another way you might have learned it in Algebra 2 is to get that a value that goes in front right there, you can do change in y over change in x squared. So to get from the origin of 0, 0, we went to the left 2, so change in y is -2, and then over x squared. Well, actually, we're going to keep it positive, I'm sorry. So we went, we did a distance change of 2, and then my y value changed by 3, so over 3 squared. Oh, I have that backwards, don't I? I'm sorry. I'm saying that all wrong. Sorry about that. My y's changed by 3, and my x's went to the left 2, and then I square it. So it becomes 3/4. So you could write that equation like this. Y equals 3 times 2x squared. Or you could say y equals 3/4 x squared. They're going to give you the same values. All right, so the way you're going to, when you write it as a piecewise function, you say f of x equals, and then you put this little brace right here. You'll write the first one, 3/4 x squared, and you're doing that for all x's less than or equal to 0. And then the other equation is the linear part, so you'll do 2x minus 4, and here you're doing all x's greater than 0. And those are your equations. Okay, that's it for these notes. Thanks, y'all.